Hello students, in this video we'll discuss topological properties of the complex plane. Let's be given the complex plane. Okay. Just see. We say that dz0 R, which is the set of points z and c, such that z minus z0 in modulus less than r is an open disk centered at z0 with radius r. Of course, the radius is a real number, and z0 is a complex number, okay? So, of course, these are the open sets. These are the basis of open sets in the complex plane, okay? Just makes the complex plane second countable. So, let's say, so here's a definition. A subset omega of C is open if for every W in omega, there is a WR, R sub W greater than 0, such that what? Such that the disk centered at W of radius RW is strictly contained in the set omega. Okay, that just means there's an open disk around every point in the omega. There's an open disk that's strictly contained in omega. Okay. All right, so it means to be open. And now let me define the notion of convergence. So I'm going to define two topological properties simultaneously, right? We also say that a sequence Zn, n goes from 1 to infinity of complex numbers, converges to a point Z in C if what? If the limit as n goes to infinity, and you're cheating using limits, but now I'm using limits of real numbers, right? The modulus of Zn minus Z goes to 0, right? So in other words, I'm defining what convergence means. Convergence means what's the definition of a limit. I'm using convergence of a set of complex numbers, and I'm relating convergence of a set of complex numbers to convergence of a corresponding set of real numbers, okay? And so what this means is the following. This just means that the points Zn are going within any sort of arbitrary small ball around Z, right? So what's happening over here with these convergence issues is if you have the complex plane, here's the real axis, here's the imaginary axis, okay? And if you have a sequence of points Zn, so here's your sequence point Zn, that just means that being closer and closer and closer, no matter how small we draw the ball, it's going to be getting arbitrarily close. I mean, I say they go over here now, give us some more space like that, okay? We just keep going over and over and over and getting closer and closer and closer and closer to here. No matter how small of a ball I draw around that point over there, those points are going to be closer and closer on the inside over there. Excellent. Okay. Now, what's an important lemma? So I claim to you, so what does this mean? So proposition. So note, let's do a note first. So note, the real part and the imaginary part, so the real part of Z is less than or equal to the modulus of Z. And the imaginary part of Z is less than the modulus of Z. Those are trivial inequalities, right? Because that's y, and that's the square root of x squared plus y squared, which is strictly bigger, right? And also, and one other inequality is that the modulus of Z is less than or equal to the real part plus the imaginary part. That's the only hard one to prove. Okay? Well, what does this say over here? In other words, this is really saying that the square root of x squared plus y squared is less than or equal to just, I have to put absolute values over here, right? Let's do it like this. There, just be completely pedantic about it. So this is modulus of x plus modulus of y. That just follows from Cauchy-Schwarz, right? And this is just a Cauchy-Schwarz application. So if I square these things, I get exactly what I want, right? So squaring this thing gives me a 2xy in here. So that just follows from Cauchy-Schwarz. Trivial. Okay. Excellent. And so now what does this tell me? This tells me, therefore, that if Zn converges to Z, so hence proposition Zn, let's write it like this. Let's write it as saying that Zn, so Zn converges, I'm going to write, how do we write this, of course? This, of course, is written Zn converges to Z. So Zn converges to Z if and only if and only if what? If and only if real part of Zn converges to real part of Z, and imaginary part of Zn converges to the imaginary part of Z. And that just follows from these inequalities. So if Zn converges to Z, then this inequality shows that the real part converges to this. If Zn converges to Z, then this inequality over here shows the imaginary part does. And finally, if the real part and imaginary part converge, then this inequality over here shows that Zn has to converge to Z. So those inequalities give me those things directly. So I encourage you to use deltas and epsilons to prove this result. But it just follows immediately from the definitions of these inequalities over here. Okay? Great. Now, we want to relate these things to Cauchy sequences, right? So definition. Zn, n goes from 1 to infinity, a subset of C, is a Cauchy sequence, is Cauchy if, for every epsilon greater than 0, there exists an n such that n in m bigger than or equal to n capital implies that what? Implies that modulus of Zn minus Zm is less than epsilon. Okay? That's what it means to be Cauchy. That's the same definition of Cauchy as it was for real numbers, right? And so now what's the conclusion? The conclusion, therefore, is that we have this important proposition, the completeness of C. Proposition. C is complete. Okay? i.e. every Cauchy sequence is a convergent sequence. Because if you converge, then you're automatically Cauchy, but then that is true. So every Cauchy sequence converges. Okay. All right, and so how do we prove this? Of course, the proof is as follows. So suppose that proof, let Zn be Cauchy. Then what can we say? These inequalities over here say what? Then automatically, well, let's be more formal about it, right? Be Cauchy, and epsilon greater than 0. Okay. Then there exists n such that Zn minus Zm is less than epsilon if n and m are bigger than or equal to n capital, okay? All right, well, that's great news, because what does this tell me? This tells me, therefore, that the modulus of the real part of Zn minus the real part of Zm, which is what? Which is the modulus of the real part of Zn minus Zm, which is less than or equal to the modulus of Zn minus Zm, is less than epsilon. What does this prove? This proves that the real part of Zn is a what sequence? Real part of Zn is Cauchy. Real part of Zn is Cauchy. Okay? And what do we know? That's a sequence of real numbers. So that sequence of real numbers being Cauchy must mean it converges. So the real part of Z what? The real part of Z converges to some number of the real part of Z. And then I can put imaginary part here, and I would say the imaginary part of Z is also what? The imaginary part of Z is also Cauchy, which means that the imaginary part of Z converges to the what? Converges to that same number over here, which says the real and imaginary parts converge. Since the real and imaginary parts converge, the sequence itself, Zm, has to converge, and therefore every Cauchy sequence has to converge. The opposite is trivial, right? If you're convergent, then you're automatically Cauchy, right? So in other words, that proves that C is a complete metric space with respect to this topology, right? And that's going to allow us to basically unlock the tools of real analysis when using Cauchy-Schwarz and using these elementary inequalities to talk about results of convergence. Thank you very much.